Okay, now we will chat a little bit about regulation of respiratory rate. Okay. Okay, so regulation of the respiratory rate. What should we start with? Well, there are two main parts of the brain stem that are responsible for this. So in medulla oblongata, there is ventral respiratory group and dorsal respiratory group. So ventral respiratory group sets up eupnea, normal breathing rate. Does that make sense? Dorsal respiratory group is responsible to adaptations. Exercise and stuff. Does that make sense? Now in pons, there is pontine respiratory group, which is also responsible for adaptations. So ventral respiratory group sets up the normal breathing rate, while dorsal and pontine respiratory groups regulate the changes in the respiration during the exercise, or singing, or talking, you name it. Does that make sense? Okay, we clear? Now, let's talk a little bit about factors that influence breathing rate and depth. So here's the thing. Think of it this way. When you start working out, like really heavy, no, that's not a good idea. Let's say you were hypoxic for a while. Do you swim? Okay, so you were swimming underwater. You were not breathing, obviously, right? You were holding your breath. Are you with me? So your tissues used a lot of oxygen, okay? Now, when you swim underwater, you can't really expel CO2 effectively. Does that make sense? So you have a lot of CO2 accumulated in the tissues as well. Am I clear? So now, when you emerge above the water, what you're going to be doing? You're going to start breathing, and you're going to start breathing harder. Does that make sense? More frequently and deeper. So essentially, two factors that substantially increase the rate and the depth increased CO2 concentration and acidic pH. These two are most important factors that increase the rate and the depth of breathing. For example, if a patient has acidosis, think of it this way. Imagine you have a patient with diabetes, okay? Diabetic patient has acidosis. Are you following me? How they want to try and get rid of that CO2 that causes acidosis, okay? So they will try to expel it by breathing harder. Am I clear? So basically, we can do this. Let's just write it down. pH drops, breathing rate and depth increase. Breathing rate and depth are increased. Are you following? More CO2 is expelled. pH increases. Am I clear? Okay. Now, if we replace pH with more CO2, this will also be a good example of negative feedback regulation. Now, why oxygen? Does oxygen play a role? It does, but not as much as these two. So when oxygen concentration in your blood goes down, in your tissues, when it goes down, it increases the rate and the depth of the breathing as well. Now, why oxygen plays lesser role than CO2 or pH? Remember when we were talking about hemoglobin dissociation curve? We figured that normally you have a pretty good deposit of oxygen. You have a depot of oxygen in the blood. You have 75% saturation of hemoglobin. Does that make sense? This is why even if oxygen levels in the tissues drop a little bit, it will not lead to the increase in a rate and a depth of the breathing. Okay? Does that make sense? Now, what about exercise? Think of it this way. There's misconception that when people exercise, their blood composition, gas composition in the blood changes. Think of it this way. Like people think like this. They think, okay, when I am running, my muscles use a lot more oxygen. Does that make sense? Which means they produce a lot of CO2. Does that make sense? So the immediate reaction will be, if I ask, how does gas composition of the blood changes when you run, people would say, oh, when I'm running, when I'm exercising, the oxygen in the blood will go down and CO2 in the blood will go up. However, this is not true. Turns out that when you exercise, okay, what happens to your breathing rate? It goes, yes. Breathing rate increases, right? Which means all this extra CO2 that's produced in the tissues is very effectively expelled. And all oxygen that tissues need is delivered pretty fast, okay, because of the extra unloading. So it turns out that levels of oxygen and CO2 in the blood as well as pH remain pretty much constant. Are we clear? So your blood pH, your blood oxygen, your blood CO2 will not pretty much change when you are running or lifting, whatever. Is that clear? Now you can ask, what is the stimulus for increased breathing rate then? Well, if you're running, it's a voluntary decision, right? So it turns out when you start running, the signal to start running also goes to your respiratory centers and sends them the signal to immediately increase the breathing rate and depth. Does that make sense? When you stop running, the signal, so it's mostly somatic regulation rather than autonomic regulation through chemical composition of the blood. So far, so good? Okay. Now, let's talk about some So do you understand why low oxygen has very little effect on the rate and the depth? Because you have a depot of oxygen in the blood. So tissue oxygen is not particularly important. Your blood always has some extra oxygen that it can deliver to tissues. So far we good? Okay. So let's mention some of the other adaptations here. So we have actually like a couple of them. First of all, shallow versus deep breathing. I'm not gonna, well, we can do that. So what is hypo and hyperventilation? Let's talk about these factors. So what is hypoventilation? In hypoventilation, your breathing rate and depth are low and they do not match the requirements. Does that make sense? Are you following? So you need you need higher rate, higher depth, but you can't for some reason. So it means that you CO2 expulsion decreases and pH in the blood goes down. This is called respiratory acidosis. Am I clear? That makes sense? Now, what is hyperventilation happens rarely, but what is hyperventilation? Okay, you're playing soccer, right? When you're running on the field, are you breathing fast? Are you hyperventilating? No, you're not. Because you're breathing fast, because you need to do that. You need to comply with oxygen requirements and CO2 expulsion of your current active state. Does that make sense?
But doesn't it feel like you're hyperventilating?
No, you aren't hyperventilating. Now, can you, listen, I'm going to give you an example. Can you imagine the breathing rate of you being on the field right now? Now, what's going to happen? If you will start breathing like this now, when you're sitting on the chair, are you hyperventilating? Dude. The term hyper means over the top, right? So, in case of hyperventilation, your breathing rate and depth are too high for the physical state you're in. Does it make sense? So when people, for instance, they stress, they start hyperventilating. So they would sit on the chair, breathing really hard like this, right? So what's the result? Breathing rate and depth go up. CO2 expulsion go up. pH increases. And this is called respiratory alkalosis. Does that make sense? Now here's an important feature to respiratory alkalosis. Check this out. When you hyperventilate, your blood pH becomes acidic. This may suppress neurons and people can end up in a coma. But when you are, hyperventilating, check this out. Breathing rate and depth go up, which results in increased CO2 expulsion, which results in elevated pH in the blood. Respiratory alkalosis. In respiratory alkalosis, the neurons in your brain go absolutely crazy. Does that make sense? If this happens in a patient who has epilepsy, patient will have an epileptic bout because of the neuronal stimulation. What if it happens in the regular person? What usually happens to people who hyperventilate, do you know? They pass out. Because neurons go completely mental in the brain. Does that make sense? How do you prevent this from happening? Take a bag. When a person hyperventilates, we give them a bag to breathe in. Have you heard about it? Breathing in the bag? So what happens? Look at this. What happens? They exhale CO2 in the bag, and then they inhale it back again. You see what I'm saying? By breathing in the bag, they maintain CO2 concentration in the blood and essentially maintain normal pH. Are you following? So basically, they do not let CO2 just diffuse away. They contain it within the bag and inhale it back. Go ahead.
But even though, like, you need oxygen, aren't you trying to get rid of the CO2 to get oxygen?
Yeah, you try. But if you get rid of more CO2 than you need to, does that make sense? Do you need to get rid of trash? Yeah. But if you start throwing out the stuff that you actually need, it's not good. Does that make sense? You need CO2 to regulate the pH of the blood. And if you start throwing out a lot of CO2, blood pH will go up, and you will have alkalosis, and you will have overstimulation of the neurons in the brain. Does that make sense? So by breathing in the bag, you can contain it. Makes sense, right? Okay, we got this hyperventilation. Now, the last little bit that I wanted to do before the break, and it's going to be very small. So it's adaptation to elevation. When you go in the mountains, the concentration of oxygen in the air goes down. That makes sense? Have you ever been to places like mountains in like Colorado? Well, honestly, I don't think I've ever been about 10,000 feet. So, kind of the same. So your first adaptation, short-term adaptation, increased breathing rate. Does that make sense? Okay? That makes sense. Now, another thing, basically increased minute ventilation. Another thing that happens in the short-term perspective, CO2 receptors decrease their sensitivity. Since you start to expel a lot of CO2, okay, CO2 becomes less important regulator of the respiratory rate. But the most important is the long-term adaptation. And long-term adaptation is increased number of red blood cells, which for you, as an athlete, can be actually very important. Look at this, listen. So imagine that which position are you playing?
Outside mid.
Okay, so midfielder. You have to run a lot, right? So take a vacation. I mean, obviously, it's more of a joke. I'm not, but if you go to Colorado or Utah or any mountainous place, preferably at the elevation of like 10 to 12,000 feet, and run there. You know, jogging. Make sense? It's going to be very hard. But do it every day. And what's going to happen over the span of even 1 week, but 2 weeks is even better. What's going to happen? You're going to have long-term adaptation. You're going to have an increased number of red blood cells. Now, increased number of red blood cells will make the oxygen delivered to the tissue is sufficient in those locations. Does that make sense? Now, after 2 weeks, you go back to Ohio. Ohio is not in the mountains, right? So you go in the field, and suddenly you realize that you have much higher endurance than any of your partners, so to say. Why? Look, because you just came from the mountains and you still have that elevated number of red blood cells. Does that make sense? If you ever look at the main training centers for runners and cyclists in the United States, they are in the Rockies. This is where they train, because when they go to compete, competitions are usually on the plains. Does that make sense? So they have that natural advantage of extra red blood cells.
So if you go from like Ohio to Colorado,
It's going to be
the first day it's going to be like hard.
it's going to be awful. Your breathing rate will go up. You're still going to have shortness of breath. You're going to get tired after like walking up the stairs. Go on, but
if you go from there here, you'll have no problem at all.
not at all. Moreover, I lived in Louisiana. I spent a week in Colorado. It was a conference. Even 1 week. I came back. I went on the run. I was flying. It was so easy because I already had elevated number of red blood cells. Does that make sense?
Does that differ with people who have asthma?
No. Oh, it's different, yeah. In asthma, it's a very short attack.
Oh, I mean does that differ for like people who have asthma? So like if I went to go train in Colorado
Mm-hmm.
and came back, would it still be as hard, or it'd be like easier?
When you have an asthma attack?
No, like you know how like I have asthma.